Both man-made and natural sources generate noise. So whether the background radiation is naturally occurring or from man-made emissions, we must protect our data communication from electromagnetic radiation. One way to reduce interference from noise is to place metal between a source of noise and a communication medium. Because metal absorbs radiation, it acts as a shield, so if there is enough metal placed between the source of a noise and communication medium, it can prevent noise from interfering. Another effective way to diminish the effects of EMI in a cable is by using twisted pair cables. To understand how twisted pairs can reduce noise, we need to understand some basic concepts. Electrical current flows over in a complete circuit. All transmissions of electrical energy all that they need are two wires to form a circuit. A wire to the receiver and a wire back to the sender. An example would be utility poles that have 3 wires that transmit powers. 3-phase is the most efficient way to transmit electrical power, and each wire carries a different phase. The wires form a complete circuit as the electrical power is transmitted from the power station to the customer and back to the power station to complete the circuit. Copper wires are typically used in transmitting electricity. Why copper? Silver is a better conductor, but it is more expensive. Copper is less conductive than silver, but it is cheaper and easier to wrap into wires, so it is often used when a large amount of conductive material is required. Gold is a good conductor and doesn't rust like many other metals when exposed to air. Gold is expensive and typically used for certain materials such as circuit board components or small electrical components. There are 3 forms of wiring that help reduce interference from electrical noise. Unshielded twisted pair, also known as UTP, and shielded twisted pair, also known as STP, and finally, coaxial cable. Twisting 2 wires makes them less susceptible to electrical noise than leaving them parallel. Why a twisted pair? This figure illustrates why twisting helps nullify ambient EMI. When 2 wires are in parallel, like the top diagram here that we have, there is a high probability that one of them is closer to the source of electromagnetic radiation than the other. When the 2 wires are twisted, one wire tends to act as a shield that absorbs some of the electromagnetic radiation, and since it is hidden behind the first wire, the second wire receives less energy. In this figure, a total of 32 units of radiation strikes both wires, in which each of the 2 cases. In the wires in parallel, the top wire absorbs 20 units and the bottom wire absorbs 12 units, producing a difference of 8. In the twisted pair example, each of the 2 wires is on top 1/2 of the time, which means each wire absorbs the same amount of radiation. This basic concept takes advantage of EMI being stronger the closer in proximity you are to the source. If the 2 wires take turns being closest to the EMI source, they will each absorb an equal amount of interference. In other words, the EMI affected both wires identically. In balanced pair operation, the 2 wires carry equal and opposite complementary signals, and the destination device detects the difference between the 2. This is known as differential mode transmission. Noise sources introduce signals into the wires by coupling of electric or magnetic fields and tend to couple to both wires equally. The noise thus produces a common mode signal which is canceled at the receiver when the difference signal is taken. Although it is immune to most background radiation, twisted pair wiring does not solve all problems. Twisted pair tends to have problems with strong electrical noise caused by close physical proximity to the source of noise, and it isn't effective against high frequencies used for communication. When the intensity is high or cables run close to the source of the electrical noise, even twisted pair may not be sufficient. In cases like this, such as in a factory that use electric arc welding equipment, or if a twisted pair runs above the ceiling in an office building on top of a fluorescent light fixture, interference may result. Multiple types of twisted pair cabling are in use. Please note some of the differences between these different categories of twisted pair cables. You can see the different max data rate and the typical application for which it is used. Coax uses a braided wire instead of a solid metal shield to keep coaxial cable flexible, but the heavy shield does not make coaxial cable less flexible than twisted pair wiring. Variations of shielding provide a compromise. The cable is more flexible, but has slightly less immunity to electrical noise. One popular variation is shielded twisted pair. The cable has a thinner, more flexible metal shield surrounding one or more of the twisted pairs of wires. In most versions of STP cable, the shield consists of metal foil, similar to the aluminum foil used in a kitchen. According to our taxonomy, there are 3 forms of media that use light energy to carry information. They are optical fibers, infrared transmissions, and point-to-point lasers. Before talking about how light energy is used in data communication, let's review how light behaves. In empty space, light travels at a speed of 300,000 kilometers per second. Light emitted from the sun travels 150 million kilometers to Earth in only about 8.5 minutes. Light does not require a medium to travel, and unlike any other kind of wave, can travel through a vacuum. However, when light travels in matter, it interacts with the atoms and molecules in the material and slows down. Light travels in straight lines in a vacuum. However, in a material medium, light shows 2 properties of reflection and refraction. When a light wave cannot penetrate an object, it reflects back, and when a light wave travels inside a medium, it bends or is refracted. The critical angle is the angle of incidence above which the total internal reflection occurs. This is particularly common as an optical phenomenon where light waves are involved, but it occurs with many types of waves, such as electromagnetic waves in general or sound waves. Total internal reflection is a phenomenon that happens when a propagating wave strikes a medium boundary at an angle larger than a particular critical angle with respect to the normal surface. If the refractive index is lower on the other side of the boundary and the incident angle is greater than the critical angle, the wave cannot pass through and is entirely reflected. The critical angle is the angle of incidence above which the total internal reflection occurs. This is particularly common as an optical phenomenon where light waves are involved, but it occurs with many types of waves, such as electromagnetic waves in general or in sound waves. Reflection explains why light stays inside an optical fiber. A substance called cladding is bonded to the fiber to form a boundary, and as light travels along, light is reflected off the boundary. The behavior of light. When an angle of incidence is greater than 0 degrees, light is reflected as if the boundary were a mirror. Light stays inside an optical fiber. At the critical angle for the material through which the incident light ray propagates, 48.75 degrees for water, the light will be totally internally reflected at the interference back into the material without passing through and undergoing refraction. Of the three forms of media that use light energy to carry information, the most important and most widely used type is optical fiber. Each optical fiber consists of a thin, hollow strand of glass or transparent plastic encased in a plastic cover. An optical fiber is used for communication in a single direction only. One end of the fiber connects to a laser or LED used to transmit light, and the other end of the fiber connects to a photosensitive device used to detect incoming light. Two fibers are used to provide two-way communication, one to carry information in each direction. So how does light travel through an optical fiber? The light in a fiber optic cable travels through the core, or the hallway, by constantly bouncing from the cladding mirror-lined walls, a principle called total internal reflection. Because the cladding does not absorb any light from the core, the light wave can travel to great distances. There are both solid core and hollow core fiber optic strands. Solid core slow the speed of light travel by 30% compared to light traveling in a vacuum. Date rates more than 50 terabits per second have already been achieved, and ultimately the hollow core fiber achievable data rate limit is above 100 terabits per second. One of the three forms of media that use light energy to carry information, the most widely used type, is optical fiber. Each optical fiber consists of a thin, hollow strand of glass or transparent plastic encased in a plastic cover. Commonly used fiber optics are the multi-mode fiber, MMF, and the single-mode fiber, SMF. Fibers that support multiple propagation paths are called multi-mode fibers. MMF cable is generally used for short-distance communication or in applications where large amounts of power are required. Fibers that support a single mode are called single-mode fibers. This tends to be the type of fiber optical cabling used in high-speed data transfer and as the backbone of the Internet. Multimode is less expensive and is used when performance is not critical or when distances exceed maximum length that copper cabling can support. The boundary between fiber and the cladding in MMF is abrupt, which causes light to reflect frequently, so dispersion is high. Single-mode fiber is the more expensive and provides the least dispersion. SMF has a smaller diameter and other properties that help reduce reflection, and for longer distances and higher bit rates.